So first question always is, are there any questions about what we did on Wednesday of last week or any of the homework problems?
Yeah, I have a question.
Go ahead.
So basically last class was just a review, right?
Right. It's a review of pre-calculus, things that you're expected to know for Calc 1. Yes.
Okay.
And the homework problems cover that.
Oh, all right.
There are homework problems for lesson 1. So the homework that's due on Wednesday is the homework in lesson 1 and the homework in lesson 2.
All right.
So lesson 1 and lesson 2 homework are due on Wednesday?
Yeah, exactly what is on the syllabus.
All right.
Exactly. And I also have a list of the homework for what lessons are due which day. So that's all on the website, and I also emailed that to everyone before class started. And the way you turn in the homework is you write out the solutions, you scan it to get a PDF file, one PDF file, and then you upload that to the assignments part of the Blackboard website. And you have to make sure you learn how to do that, because that's exactly how you will do your exams and turn in your exams.
The homework is due by the end of the day on Wednesday?
Yes.
Before class?
No, anytime on Wednesday.
Okay, thank you.
And the grades are always available on the Blackboard website. All right, well, if there are no questions, then today's lesson is on limits. So a limit is the fundamental idea in what is called a mathematical analysis. And let me just start with a kind of a geometrical example. In high school or somewhere, you learn about circles, and you have the idea of a tangent line to a circle at a point on their circumference. And in geometry, you learn a lot about tangent lines. If you take the center of the circle, for example, and you draw the radius from the center to a point on the circumference, the tangent line is always the unique line is perpendicular to the radius. But the way you get the tangent line, or one way to get the tangent line, is as follows. If you take your circle, let's say you want the tangent line at this point. So here's some point P, this is the center. You might take another point on the circle different from P, call it Q, and draw the line from Q to P. So that's what is called a chord. A chord is a line through two different points on the circumference of the circle. Right? And so here's the point Q, here's the point P, you draw the chord. Now let's call this Q1. Let's say you take another point on the circle between P and Q1, call it Q2. And you draw that chord. And then you take a point Q3 even closer to P, and you draw that chord. And if you take a sequence of points, Q1, Q2, Q3, and so forth, on the circle, getting closer to P or approaching P, we get the sequence of chords through each point P sub n, Q sub n, and P. So for every one of these points, you have a chord, and the important sort of theorem, or if you like, definition of a tangent is the tangent line is the limit of the sequence of chords. So saying this because it gives you a kind of a geometrical way to picture an example of a limit. Namely, you have all these different lines on the circle going through the point P, through a point P and a point Q, and as the point Q gets closer and closer to P, this sequence of lines is always moving, and it's getting closer and closer to a certain fixed line, and that fixed line is the tangent. So these lines are getting closer and closer and closer to this line. So that is a geometrical example of a limit. Now, what happens in calculus is we want to generalize this notion of the tangent to a circle. Suppose we have a function y equals f of x, and it has some kind of graph. And let's say at some point on the graph, here is x equal to c. So this point has coordinates c comma f of c. We could do something similar. We want to find, so we want to construct or define the tangent, that means the tangent line, to the graph of y equals f of x at the point when x equals c and on the curve y is equal to f of c. And what we're going to see in a couple of weeks is, think of this as a point P. If you take a point Q different from P and draw this chord, by that I just mean the line through those 2 points. And if you take a sequence of points different from P but getting closer and closer to P, this sequence of chords is going to approach a line, and that line is what we're going to call the tangent line to the curve at the point. So a large part of what we do in the beginning of calculus is learn how to generalize the idea of a tangent to a circle to a tangent to a point on an arbitrary curve defined by some function y equals f of x, if we can do that. Of course, you can't always do that. If you take, for example, the function f of x equals the absolute value of x, that's what the graph looks like. It has this corner at x equals 0. And so this function has there's no way to define the tangent to this absolute value function at x equals 0. So we're going to learn that we would like to always be able to define a tangent line. Sometimes it's not possible. And it's also important to know when it's not possible. And all of these processes of constructing something like a tangent line involves the notion of a limit, and that's what we'll talk about next. Are there any questions about this so far?
Yeah, I have a question, but it's mainly just the writing.
No, go ahead. Just speak up because you're a little bit soft.
Can you hear me better now?
Yes.
All right, no, graph of y equals f of x at, what are those points again?
Well, it's some value of x. Let's call it x equals the number c.
All right, thank you. That's all.
Someone on the chat just asked a question about how many of the homework problems you're expected to do. So the principle is the more you do, the more you learn. And if you can do them all, that's the ideal thing. If you can't do them all, then make sure, let's say there are 20 problems in the homework assignment, make sure you just don't do the first 6. Because the first 6 are probably on just one topic that's being covered in the assignment, and you'll miss learning how to do other things. So if you're going to do just some of, but not all of the homework problems, make sure you jump around and do different problems on different topics, so you get the experience of learning a little bit about how to do everything. That's the idea. Okay, so limit. So suppose we have a function y equal f of x, and informally we say that, then this is the notation we use, the limit of f of x, and under limit, which you just abbreviate LIM, you write x arrow c equals L. So the way we read this is the limit of f of x as x approaches c is L. This means, this is approximately, f of x gets closer and closer to L as x gets closer and closer to the number c. Okay? And we don't let x ever equal c. That's whatever the value of the function of is at x equals c is irrelevant to us. What's important is that as x gets closer to c, f of x gets closer to L. And in a little bit, I'll write down a formal definition of this. But intuitively, this is what it means. So here's an example. I'll call this example 0. Suppose we let f of x be the function x cubed minus 1 over x minus 1 for x not equal to 1. Why x not equal to 1? Because if you were to let x equal 1, you would get a 0 in the denominator, and that's not, you can't divide by 0. So the domain of this function, the set of the values of x for which f of x is defined, is all real numbers x except x equal to 1. And you can do a calculation if you like. Suppose we want to, so we ask the following question: what is the limit as x gets closer to 1 of f of x? Now, one possible answer is it gets closer and closer to the number 17. Or it gets closer and closer to the number 3. Or the limit does not exist, right? Each of those is a possible correct answer. We have to find out what it is. Now, if you were to take your calculator and compute this, I mean, you could make a sort of a table of, for different values of x, what is f of x equal to? So as x gets closer to 1, you could let x be maybe 0.75 or 0.9, that's even closer, or 0.99 or 0.999. And the book makes a table of the, it just actually, you know, you take out your computer or your calculator, you plug these numbers into f of x, and what the book gets is 2.313, 2.710, 2.970, 2.997. So these are certain values that are getting closer to 1 from below. These are numbers less than 1. Or you could look at numbers bigger than 1. You could have 1 and 1.25, or 1.01, or 1.001, or 1.0001. No, forget that one. 1.1. So if you look at the table in the book, you get certain values. When x is 1.1, it's 3.31. When x is, give myself some more space. So this is at 1.1, 1.01, 1.001. At 1.01, this is 3.03. At 1.001, this is 3.003. And it looks like as you approach the number 1 from below or from above, the limit of f of x looks like it's getting closer to 3. This is not a proof. This is just some numerical evidence. And in fact, this is true. And we can actually explain why this is true. So here is a proof that the limit of f of x for this function as x approaches 1 is equal to 3. Here's the function. We can factor x cubed minus 1. This is x cubed minus 1 is x minus 1 times x squared plus x plus 1. How did I factor that? Because high school algebra is a prerequisite. In high school algebra or pre-calculus, you learn to factor. So I can divide by x minus 1 for x different from 1. X cubed minus 1 over x minus 1 is x squared plus x plus 1 for x not equal to 1. So this function that I'm looking at for x not equal to 1 is equal to x squared plus x plus 1. And as x goes to 1, x squared goes to 1, 1 goes to 1, this goes to 1 plus 1 plus 1 equals 3. So that's actually a proof that this limit is equal to 3. Are there any questions about that? On the chat, I see someone asking where to send the homework. Again, if you go to the Blackboard website from this course, this section, Math 175, under assignments, each homework is listed. You click, for example, on homework 1, and it will prompt you to upload the PDF file of your homework. That's how you do it. Okay. Here is example 2 in the text. Suppose we define the function f of x as follows. For all x different from 2, the function is equal to 1. And when x is equal to 0, And when x is equal to 2, the function is equal to 0. What does the graph for that function look like? When x is 2, the function is equal to 0. When x is different from 2, it's the constant function 1. So this is the graph of the function. As you start at minus infinity and you move to the right, you're moving along this horizontal line, y equal 1. When you get to 2, it jumps down to 0. And then to the right of 2 out to plus infinity is equal to 1 again. That's the graph of the function. So for this function, what is the limit of f of x as x approaches 2? Well, the value of the function at 2 happens to be 0. But when x is different from 2, the function is 1. And as you get closer and closer to 2, the function is still 1. It's always 1. So the limit as you get closer and closer to 2 is equal to 1. It's not equal to 0, right? No matter how close you get to, or when you get very, very close to 2, the function is 1. So you have this function is 1, 1, 1, 1, 1, and the limit is 1. The fact that the value of the function at x equal to 2 is 0 is truly irrelevant to us. Okay, questions? Someone asked about these pages that I'm writing out. These are all on the YouTube website. The YouTube website consists of these pages and my voice and the lecture. So if you want to review any of this, you just go to YouTube and you look at the lecture. Every lecture is posted on YouTube, on the channel for this course. Okay. Example 3. Suppose we take the function f of x equal to the absolute value of x for x not equal to 0. Again, you can't divide by 0, so this function is not defined for x equal to 0, but everywhere else it is defined. That's what it is. What does the graph of this function look like? If x is greater than 0, then the absolute value of x equals x. So the absolute value of x over x is 1. If x is less than 0, then the absolute value of x is minus x. This arrow with double-headed, this double arrow means implies. So if the absolute value of x is minus x, then the absolute value of x divided by x is minus 1. So if you look at the graph of the function, y equals f of x, at 0, it's not defined. For positive values of x, it's 1. For negative values of x, it's minus 1. And it's not defined at 0. So what is the limit of f of x over x, f of x, absolute value of x over x, as x approaches 0? Well, if you take values of x that are positive, it's always equal to 1. So as you approach 0 from the right, the limit of the function is 1. But if you take negative values of x, f of x is minus 1. And as you approach 0 from the left, the limit is minus 1. They're different. So what can we say about this limit? It does not exist. There's no number that's the limit of this function as you approach 0. You might say there's a right-handed limit. There's a limit from the right, which is 1. You will sometimes write that the limit of x goes to 0 from the positive side is equal to 1. The limit as x goes to 0 from the negative side is equal to -1. So like the right-handed and the left-handed limits exist, but the limit does not exist. Okay. So this is an example. This is our first example of a limit that does not exist. Example 4. Suppose we take the function f of x equal 1 over x squared. Again, it's only defined for x different from 0. For x different from 0, positive or negative, x squared is positive. So this function is always positive. And what does the graph of this function look like? Well, it looks like this. As you go out to plus or minus infinity, it's decaying to 0. And as x approaches 0, this is going up to plus infinity. So the limit of f of x as x approaches 0 also does not exist. Some people like to write, it's equally true, slightly more precise, the limit of f of x as x approaches 0 is infinity. But if the limit's infinity, then it does not exist. It just means it's getting bigger and bigger and bigger. This is chapter 2, section 2 in the textbook. We follow the syllabus always. So this is the second class, it's lesson 2. You look at the syllabus, and then the syllabus says lesson 2 covers chapter 2, section 2. So you always know what section we're doing by looking at the syllabus. That's why we have a syllabus. Okay. Any questions? Let me just pause for a second to make a note of attendance. Okay. Someone asked, is there a preference or what edition of the textbook? I would say get the cheapest one, because the book's overpriced, like every calculus book. The syllabus is based on the 5th edition. If you have the 4th edition, it's okay. If you have the 6th edition, it's okay. I would just try and not have to spend too much money on the book. But it doesn't.
I have a question.
Yeah, go ahead.
So are the books available only on campus, or can I like buy them online, like Amazon?
Oh, no, it's a standard calculus book. So I don't think you can buy it on campus. They won't let you on campus, will they? I mean, campus is supposed to be closed. Students aren't, in fact, I'm not allowed on campus. I don't think students are allowed on campus unless they are taking maybe a laboratory course where they have to be physically present in the laboratory to do the work.
The reason I asked the question because last class you had the book and it said Lehman edition on it, so I got confused. Sorry.
No, there was some Lehman edition. I don't know why they did that, or why, because it just makes it harder to sell the book if you have it. But any edition is okay. And there's also, I believe, an online edition. So you don't get the physical book, you get the, well, you get it online. You get you can read it on your computer. And there probably are multiple options about that as well.
All right. So like a PDF version of it.
What?
So like a PDF version of it.
Yeah, I mean, again, I don't know. I mean, if there's a Lehman edition, it's supposed to be cheaper, but maybe that's when it was new and being sold in the bookstore a couple years ago. So it should make no difference whatsoever which edition you have. The text is basically the same. The problems might be slightly different, but they will still cover the material. And that's the important thing.
Okay. Thank you.
Yep. Okay. Example 4 has to be followed by example 5. So here we have the function f of x equals the sine of 1 over x. And again, the domain of this function, where this function is defined, is only for x different from 0. If x were equal to 0, this wouldn't be defined. What does the graph of this function look like? So you know what the graph of y equals the sine of x looks like. It's this beautiful oscillating function. Right? But this is not the sine of x. This is the sine of 1 over x. What does the graph of y equals the sine of 1 over x look like? Well, this is a little bit more complicated. As x gets bigger and bigger and bigger, so as x goes to infinity, then 1 over x is going to 0. and x is positive. So as x goes to 0, so as 1 over x goes to 0, the sine of 1 over x is approaching 0. So this function is sort of decaying to 0 as x goes to infinity. But we want to know something about the limit of the sine of 1 over x as x goes to 0. Now, as x goes to 0, one over x, that goes to plus infinity. So this function is going to start oscillating faster and faster and faster as you approach 0. Similarly, as you go to negative infinity, the sine of 1 over x is going to 0 and it's negative. So you're approaching 0 from below. But as x approaches 0 and x is negative, 1 over x is still going to minus infinity. This function is oscillating. So what you have as you approach x equals 0, the y-axis, is this tremendously oscillating function. It has no limit. So this limit does not exist. Okay, so we spend a lot of time in the beginning of calculus computing different limits because everything in calculus is a limit. The two main operations in calculus are computing the derivative of a function and the integral of a function. And they're both defined as limits. So we should have, for the record, the formal definition of a limit. When I took calculus, you actually had to memorize this. You really needed to know this precisely. For us, that's not necessary. For us, we just need to have a good intuitive understanding of what a limit is and techniques to calculate it. But it's important to know there is a definition of a limit, and here it is. So let f of x, or let f, be a function defined on an open interval containing some number c. Except the function doesn't have to be defined except. Possibly at c itself. What is an open interval? An open interval, you write it a comma b with a and b in parentheses. This is all x such that x is between a and b, but not necessarily, but it doesn't include the endpoints. So the open interval between 2 points a and b is all numbers that are strictly greater than a and less than b. That's why it's called open, because it doesn't include the endpoints. So when we say the limit of f of x as x approaches c is equal to L, if, so this is the official definition, for every number, we use Greek letters, epsilon, greater than 0. So this is the Greek letter epsilon. So for every epsilon greater than 0, there exists a number delta, that's the Greek letter delta, greater than 0, such that if the distance from x to c in absolute value is less than delta and greater than 0, then the distance from f of x to L is less than epsilon. So if you want to draw a picture of that, that would mean the following. Here's the number c. You have the graph of your function. And if you take, so for any epsilon, and let's say this is L. So if you take any epsilon, you can go from L minus epsilon to L plus epsilon. That's some open interval on the y-axis. And so to say that if x is within delta of c, x minus c less than delta means if you take a number x in this interval, not necessarily at c, the graph of your function is always between these two red lines. It's always in this rectangle. So for any x within a distance delta of the number c, f of x is within a distance epsilon of L. So this is a formal official definition of a limit. And if you're going to be interested in mathematics, or certainly a math major, you really need to spend a lot of time trying to understand the definition. But the definition is not anything that you're ever going to be asked. What you will be asked to do is to calculate limits, and you'll spend a lot of time doing that. Okay. All right. So that is our notion of a limit. And there are a number of exercises, homework problems, which are due on Wednesday, having to do with limits. There's one other topic in the syllabus for this course that I should cover today, and that is part of our pre-calculus review. It is the notion of an inverse function. So I just want to now begin to talk a little bit about section 1.5. Inverse functions. So you can think of it, if you like, as follows. Suppose we have some function f, and here is the domain of f, and here is the range of f, and our function f sends every point f, x in the domain, to some number f of x in the range. What does it mean to have an inverse function? It means that, so let f be a function from whatever is its domain into its range. Suppose we have another function g that goes in the reverse direction. Suppose we have a function g that goes from the range of f to the domain of f. So here is the definition. F is G is the inverse function of f if the following two conditions hold. So for every x in the range of f, which is going to be the domain of G, we can take X, compute G of X, and then compute F of that, and we get back X. And second, for each X in the domain of F, which is going to be the range of G, if I take X, I send it over here, I get F of X. I take F of X and I apply to G to that. That brings me back over here, and that's equal to X. So the inverse of a function somehow reverses the function. Okay. So what are some examples? Well, suppose we take F of X equal to X plus 1. I claim that the inverse is G of X equal to X minus 1. So I claim this is the inverse function. And we often denote the inverse function denote the inverse of F by F to the power minus 1. So this doesn't mean 1 over F, this means the inverse of F. So well, let's just check. What is F of G of X? Well, G of X is X minus 1, so this is F of X minus 1. And if you plug X minus 1 in here, what do you get? You get X minus 1 plus 1. The ones cancel, you get X. So F of G of X equals X. And what about G of F of X? That's G of X plus 1. That's X plus 1 minus 1, or X. So G of F of X is equal to X. So F inverse, if F is X plus 1, F inverse of X is X minus 1. Okay. That's a simple example of an inverse function. What's another example? Well, suppose we have F of X equal to 2x cubed minus 1. What does the graph of that look like? When X is 0, this is minus 1. When X is 1, this is 2 minus 1, it's 1. When X is minus 1, this is minus 2 minus 1, it's minus 3. And in fact, the graph looks like that. Suppose we let G of X be equal to the cube root of X plus 1 over 2. That looks a little bit complicated perhaps, but let's see. What is f of g of x? So that's f of the number cube root of x plus 1 over 2. What does f do to a function? To a number, it takes, it's 2 times the number cubed minus 1. What we're cubing is the cube root of x plus 1 over 2. When you cube a cube root, you just get x plus 1 over 2. 2 times x plus 1 over 2 is x plus 1 minus 1 is equal to x. So f composed with g is x. What is g composed with x? What is g of f of x? That's g of 2x cubed minus 1. That's the cube root of this 2x cubed plus 1, 2x cubed minus 1, plus 1 over 2. The 1's cancel, the 2's cancel. This is the cube root of x cubed, that's x. So we have an inverse function. So on chat, there's a discussion. What happens if you don't have the 5th edition? And I keep saying it doesn't matter. First, the text is the same. They basically don't change the text. All they do is maybe they add 1 or 2 problems. So the problems might be numbered slightly differently. But the problems will still cover the material. And the idea is it doesn't matter what problems you do, really, so long as you're doing problems that cover the material. And so do the problems, and if you have a question about a problem, just ask me in class. Every class starts with my asking you if there are questions. And I'm happy to do any problems, no matter where they come from. So let's look at another example. Suppose we have f of x equal sine of x. Compute an inverse function. Now, what does the graph of the sine of x look like? Well, it oscillates. At every multiple of pi, you get 0, for example. So suppose some function g of x is the inverse function of the sine. So what is g of 0? So that means if we took f of g of 0, we would get 0. So g of 0 would have to be some angle whose sine is 0. But f of g of 0, well, so g of 0, it's some angle whose sine is 0. So that could be 0, pi, 2 pi, plus or minus pi, plus. It's not defined. There are too many different choices. And the reason is, if you would take a number like 0, there are infinitely many different angles that give you that value. Just as if you take, for example, the number 1, what angles have sine equal to 1? Well, pi over 2, 5 pi over 2, minus 3 pi over 2. There are lots of angles whose sine is 1. So there's no way to compute an inverse function for the sine over all values of x. But if you just look at the sine between minus pi over 2 and plus pi over 2. So here is f of x equals sine x for x between pi over 2 and between minus pi over 2 and pi over 2. So here's pi over 2. Here's minus pi over 2, 1, minus 1. In this interval from minus pi over 2 to pi over 2, this function is strictly increasing. It's going bigger. It goes from minus 1 to 1. So if I take any value of y between minus 1 and 1, there's only one angle, x, in this interval whose sine is equal to that number. So an inverse function exists in this interval. And it's denoted by g of x. It's sometimes written as arc sine of x or sine inverse of x. This gives you the angle whose sine is equal to x. And the graph the graph of the arc sine or the inverse sine would have to look like this. The range, the domain of this function is from minus 1 to plus 1. And the range is from minus pi over 2 to plus pi over 2. And it looks like this. So this is the graph of y equals inverse sine of x. That's the graph of y equals plus the sine of x. And this inverse function does exist. In general, an inverse function exists if in the domain of the function, a number value y is the value of the function at most one time. This is sometimes called the horizontal line test. If you were to draw any horizontal line, it crosses the graph at most one point. If you took all of the sine of x function, any horizontal line will cross this curve at infinitely many different points if it crosses at one. So this graph fails the horizontal line test, but this graph passes it. If we only look at the domain of the sine from minus pi over 2 to pi over 2, a value of y is taken on at most one time. Sometimes it's taken on 0 times, but at most one time. Okay. So the homework that's due on Wednesday, again, you have to look at the syllabus and you have to look at the, I actually have, which I emailed to everybody and is on the website for the course. It says what homeworks are due on what day. So on Wednesday, the homework 1 covers lesson 1 and lesson 2. Generally, every homework covers 2 sections. So the homework for lesson 1, lesson 1 I did on Wednesday. Lesson 2 I just finished. The homework for this Wednesday consists of 2 homework lessons, lesson 1 and lesson 2. Okay. Any other questions? If not, then we're going to stop because I just covered everything in lesson 1 and lesson 2. I want to wait until Wednesday to start going over homework problems. I don't like to go over homework problems too much before they're before the day that they're due, but that's where we are. Any questions before we close? Okay. If not, then we are done, and in 10 or 15 minutes, I will have uploaded this lecture to Blackboard, to the YouTube website. All right. I will, again, I also have an office hour today at 1 o'clock on Zoom. The Zoom login is on the website. So I'm available then if you have any questions. Mainly count attendance using homework. Yeah, I also sometimes look at attendance at lectures because I'm curious to know how many people who's watching the lectures. Also, I know that in general, coming to class correlates with learning the material and getting a good grade. Someone's asking whether it's possible to keep us updated with assignments and stuff with announcements. The assignments are posted for the whole semester. There's no update that's needed there. If anything changes, I'll certainly send it out. But you already have every assignment for the course. Okay. Anything else? Going once, twice? All right.
Office hours are at 1, right?
Yes. And it's a different Zoom login, but it's on the website for the course, and I emailed it to you previously.
All right.
Okay. Bye, everybody.